I'm going to work some examples where we'll take a system. We may, on some of these, be given a bond graph that's already complete. You should go through the process. I'll quickly verify this graph for you, but you should again use these as exercises to practice building a bond graph. On some of these I won't have a bond graph and we can build those together. This is an electric circuit. I'm going to assume all linear elements here, so I'm showing an inductance, resistance, capacitance, resistance. I would probably number these according to the bonds, which I've already put numbers on these bonds here. But you can see I've got an effort source. So if this is some voltage, say source of effort, that would be the effort here. There's a common current with this inductance. So this inductor here, and for example, I would put that L2 if I wanted to parameterize and show that that's the inductance on bond 2. That's L2 here. You can see R. This is going to be R3 here. So if I wanted to fully annotate the bond graph, this is going to be R6, and so that would be R6 there, and then this is going to be C5. Okay. So I've got the bond graph, and let's apply causality. So I've got an effort source here. I've got two energy storage elements, no other input. So that causality is effort in. So I can then start propagating at a one junction. One bond given effort does not force any causality. So I am free to apply integral causality, giving me an independent energy storage element here. So call this lambda 2. The state on this I element, this inductor, is going to be a state of the system. So I'm going to start creating over here my state vector, and already I've got lambda 2 there based on that first integral causality. Okay. So now I've determined the flow here, and this is current I2. Again, that's the current that's common there. And now that I've specified flow at that one junction, all of these have to be efforts onto that one. Okay. The voltage across 3 here is that resistance, is that voltage drop across that resistor there. But I3, the current through there, obviously is equal to I2, and so on. So sometimes I don't fully annotate the graph because, for example, here on this one junction, I know all these currents are the same. Unless you just want to put it down there for yourself, you should know that on a one junction all these currents are the same. There's no sense writing them all down. And I sometimes actually will look at the causality and say, oh, this bond here is determining the current of that one, so that might be the only one that I write, because that's going to be sort of the go-to current where I'm going to that I'm going to use when I start writing my equations. Okay, keep that in mind. So I've assigned all the causality here, so now I can move to my next energy storage element, because there's no other way to propagate causality from the assignments I've made. So I'm free on this junction here to give integral causality to this C element. So the voltage 5 is going to depend on the state of this capacitor, which is Q5, but remember this is the flow here, so I have to put the rate of change of that state. And because I have integral causality again, my Q5 is a state of the system, right? So here's my state vector, and so n equals 2. It's a second order system. So how many equations do I write? 2. And let's start writing those. Okay. So the first equation I'm going to write is for lambda 2. Right? Remember, that's the nice thing about identifying the states, is that you know right away what equations you need. So the state is lambda 2. The state equation is the rate equation, which is lambda dot 2. And that's equal to the effort, which is a voltage on bond 2, right? That's the effort that's coming in from the one junction into here. And V2, and remember, I'm going to use my sum of efforts around the one junction to give me V2, and that's equal to what? Vs, and that's a known input, so I'm going to write that as a function of time, minus V3 minus V4, right, which is that bond here, right? So there's my equation. And the whole game then, from here on out, is going to be writing everything on the right-hand side here in terms of states and inputs. This is an input, so I really need to just focus on getting rid of V3 and V4. So V3, I know, is this voltage, and I know because I've got this resistor that that's just equal to R3 times I3, which is the current through the resistor, right? But what do I know about I3? I know that it's the same as all the currents here, which is, so what is I3 equal to? Read the causality. I3 is determined causally by I2. Okay? Now why is that important? Because remember, I2 is coming from the inductor, which is an independent energy storage element, which means I2 can be determined in terms of what? State, right? So I2 is equal to 1 over L2 times lambda 2. Where did that come from? This is the constitutive relation for my inductor. So back substitute I3 into here, gives you V3, put it in here, and that's this term. Finally, V4. Where is V4 coming from? Read the causality. V4 is the effort coming from the zero junction. Now, which bond of these three is determining the effort at that zero junction? It's not these two. These are determining flows. It's this one, right? It's coming from the capacitor. Okay, so V4 causally, right, is equal to V5, which is what? The voltage on the capacitor, which is 1 over C5 times Q5. That's a state. So I've determined both terms, V3 and V4, in terms of states of the system. Once I back substitute everything into here, I can write lambda dot 2 in terms of inputs and states, and I'm done. And I'll let you finish that part. Okay. The next, so that's the state equation for lambda 2. What's the state equation for my other state? Is Q5. That's Q dot 5. And that's equal to the rate equation here, which is equal to the current I5, right? Now, what is I5? Now, what is I5? That's the current into that capacitor. And where does that come from? Remember, the flows at a zero have to sum. So I5 is coming from I4 minus I6, right? So I5 is equal to I4 minus I6. Now those aren't states and they're not inputs, so I need to write those in terms of states or inputs. By the way, I didn't finish my causality over here, right? I should have done that, right? Because that's the effort here, that's the effort into the R junction, into the R element, sorry. Right, so what is I4? That's my first one here. How do I find I4? Well, I4 is the current here. Which bond is determining that I4? It's coming from that one junction. Which bond is determining the, which bond is determining the flow at this one junction? And that's I2. Remember, always come back to I2. Why? Because I2 can be expressed in terms of state. Right? So I've got I4. How about I6? I6 is coming from this resistor. How do I find I6? Well, I use the constitutive relationship that says that I6 is, if it's a linear resistor, is 1 over R6 times V6. But what is V6? Again, you're going to get tired of hearing me say this. V6 causally is equal to the voltage at this common effort junction, which is determined causally by this bond, which is V5. That's important because what? V5 is, as I found here, a function of state. So I6 is 1 over R6 times C5 times Q5. And I'm done. So now I have found I4 and I6. So the right-hand side of this state equation can be expressed in terms of these two states, lambda 2, Q5, and parameters. What you do then is write your state equations in full form. It would be lambda dot 2 Q dot 5 in vector form, and because these are linear, you can put it in linear state space form. Right, lambda dot 2 would be, and you're going to need your input also. There's only one input, so I can pull it out of here. So lambda dot 2 is equal to what? 1 times Vs of t, but then it depends on lambda 2 with this term here, and it's got a negative in front of it. So lambda dot 2 is minus what? R3 over L2, right? Times lambda 2. And that's the term here, and then the second term would be V4 here, minus V4, which is minus V5, which is minus 1 over C5, and so on. And I can let you finish and get these two terms here in terms of Q5. Since Q dot 5 doesn't depend on Vs, this term here is a 0, right? So here's your linear state space equations, if you need to write them that way. And remember, we can only write them in terms of these matrices because they're linear. So this is a linear system. So these are what we call linear state space equations. Practice this more in other examples. Consider this example hydraulic system. We have two tanks with constant area, showing that there's a pipe in between with some resistance. We can assume it's a long pipe maybe, so it's got some inertia. Maybe there's some flow coming in here. Maybe this is a big reservoir or big tank with some rain coming in. There's no flow coming into here. And let's say that that we've got a controlled pump here, so that we can control, say, the output here as a function of time. And we're trying to control, let's say we're trying to build a control model. We got some flow coming here. We have a tank, an intermediate storage tank here where we can pull it out, but we are also pulling out here to atmosphere. We'll build a model. We'll make assumption that these tanks have common pressure down here. This is again a long pipe, so we've got some inertia maybe here. So let's indicate I here, and maybe initially, let's not put any resistance on there, because this could be turbulent. So, but there is some resistive effect here. So we'll just say that there's some losses, and we'll leave that nonlinear. Okay, so let's build a graph for this, and then I'm going to get the equations started for you, but I may not derive them completely, and leave that as an exercise for you. So we've got this tank here. So what I'd like to do is, you've got flow that's leaving here, flow coming in, so and then this flow being accumulated. So we know that we can throw a 0 down, and we've got some flow coming in as a flow source from this rain. We've got flow being accumulated in a tank, and then we've got some leaving. The flow that enters has to leave, so the flow that's coming in is equal to the flow coming out, but there's inertia and there's some losses. So what do we need? We need a 1 junction, and we need to represent the kinetic energy storage and some loss effect here, right? And so the flow that's coming into here and then leaving is the same, so it's a 1 junction. But then there's some kinetic energy here that's being stored in this I element, and then it drops into another 0, right? Because we've got another tank and another C, and then finally we've got another flow source because I'm controlling this guy here. Okay. Okay, so that's we can number the bonds, make it easier if you like. 1, 2, 3, 4, 5, 6, 7, and 8 here. I still like to use physical variables, so there's a pressure here. I'd like to indicate possible states. I have 3 energy storage elements. I have 2 sources, but I have a volume here, V dot 2, and a volume here, V, and I need a rate of change of the volume. The volume is V8, but then this is the flow, right? The rate of change of the state. And then here, remember we use gamma 4, and then I need the rate of change because it's the pressure. Those have to be efforts and flows, right? And then Q4 is the flow associated with that state. Okay, so here you have my graph, and let's apply causality and determine the number of states we need and the number of equations. Okay, so I have a flow source here and here, and so I have to start with one of these sources. I'm going to go ahead and start off with this one. That has to be a flow in, right? I come in with a flow into a 0 junction, and remember that does not constrain your causal assignments. It doesn't propagate through. A flow into a 0 junction does not mean that you are constrained to assign these in any way. So you have to stop there and look for other sources before you start looking at energy storage elements, because we know we have another source here, so I need to come in and put my causal stroke here for flow. Remember, here's another case where I have power flowing in this direction. Flow is being specified in causality, power, 2 different assignments. All right, and again, that's causality of a flow into a 0 junction, so I'm not constrained. So now I start looking for other sources. I don't have any, and now I can look at my 3 energy storage elements. And since I have a C here, I'm going to start with that one, and I want integral causality. And what is integral causality? I have flow in, so let's assign flow in here, which means this is independent. So I'm going to create my little state vector over here, and V2 is a state of my system, right? Once I make this causal assignment on bond 2, that means no other bond can specify effort in there. It's already specified by this tank, and so this has to specify a flow. So now I have to propagate that into this 1 junction. An effort on a 1 junction, right, doesn't impact it. I can go to any of the other bonds to specify flow into that, and now I can apply integral causality on my I element. So that means that what lambda 4 is the state. Now I've assigned flow there, so these two have to be efforts in, just like this one. Here's my flow. So what does that mean? It means that all the flows here are equal to Q4, determined by state. Now I've got a flow going into the zero, I've got another flow going into the zeros. Now I am forced to apply flow effort from here, which is good because now I've got my final independent energy storage element. So I've got 3 of them. So I've got 3 independent energy storage elements, which implies n equals 3. The 3 states are the states of the system. Final one here is what? V8. Okay, so the next step would be to derive each of the equations. And I'm not going to derive these completely, but I will start for you. Sorry. Let's go ahead and get the state equation for V2. Remember, it's the state equation is the rate relation, which is V dot 2, and that's equal to the flow on bond 2, which is equal to, from the zero junction, and using the sign, QR minus Q3, which is bond 3. This is an input. Let me go ahead and put a function of time minus Q3. But Q3, this is Q3 here, is equal to causally Q4. Let me draw this, show you, like, one thing that you can visualize is that the causality tells you that that flow information is coming from this bond. Okay, so Q3, right, I like to think of Q3 then is equal to Q4, and Q4, right, is 1 over whatever that I4 is times lambda 4. That's the constitutive relation for the inertia in here, and this is I4. Okay, and so note this is an input. Q3 can be written as a function of state, and that state equation would be done. Okay, V dot 8 over here is going to be very similar. You're going to have Q6 here, which depends on Q4 minus Q0, so that's very similar. I'm not going to write that one for you. I will write it. Let me just write V8. So the rate relation is V dot 8. And that's equal to Q6 minus Q0 of t, and you can do that one. Find that term. The last one is gamma 4, and that's a pressure equation, right? Gamma dot 4. Now I need to look at this little relation here, and that you're going to have to sum the efforts around that one junction. Okay, and that's gamma dot 4 is equal to P3 minus P5. Remember, I'm putting the sign in there based on the sign of the bond here, and this is P6. Okay, so verify for yourself that gamma dot 4 from the sum of the efforts there is equal to P3 minus P5 minus P6. Important to get the sign right here. The game here then is to write each of these terms as functions of state. Okay, and P3 is the pressure here, and so you need to determine that P3 by the causality is equal to what? It's the pressure on P3 is coming from the zero junction. The pressure at that zero junction is determined by P2, which is going to be a function of V2, right? So P3 is equal to P2. And because you know P2 depends on V2 through the constitutive law for this tank, you got that one. P5 is, use the resistance. We don't know that one. So I'm going to say it's a nonlinear law, but it depends on Q5, right? And Q5 is what? Q4. Why Q4? Because causally Q5 depends on Q4. Okay, and Q4 depends on lambda 4. Okay, so you need to know this function for this resistor. Is the flow laminar? Is it turbulent? That's going to determine this function. Lastly, P6. What is that? Well, that's coming. Verify it. It's coming from P8, which depends on V8. Finish that in complete form. Since these are nonlinear because of this form here, you would not be able to write these in linear state space form, but you could write them as linear state equations in the form of functions of the states and the inputs.